In this video, I aim to answer the age-old question, what are generative adversarial networks? Generative adversarial networks, also referred to as GANs, are algorithmic models that use two neural networks pitted against each other in a game-theoretic scenario in order to generate synthetic instances of data that can pass for real data. Data inputs and outputs can consist of songs, pictures, websites, and even videos. GANs consist of a generator model that we train to generate new examples, and the discriminator model that tries to classify examples as either real or fake. To try to make this idea easier to understand, I have devised a hypothetical scenario composed of a student and a teacher. Imagine that a student, let's call him Bob, is in detention, and a teacher, let's call him Morty, is supervising him in detention. Morty gives Bob a challenge. He says, if you can transform into the image of a perfect student, I will release you from detention early. If not, I will keep you here forever. Mwahahaha. Disclaimer, it is worth mentioning that Bob has special powers that allow him to shift his physical makeup at will. Bob and Morty serve as the roles of the generator and discriminator models. Bob, as the generator model, needs to use his super cool, amazing transformation powers, trademarked, to generate himself into a person that can trick Morty into thinking that he is a perfect student. The problem is, much like normal generator models, Bob has no idea what constitutes a perfect student. In comparison, Morty, has inputs from his previous years of teaching on what constitutes a perfect student. And I'll tell you right now, young Macaulay Culkin does not fit that description. This idea of inputs from previous years represents a training set that is given to discriminator models that is then used to make decisions on whether the generated data is real or fake. Looking back at our example, let's say that Bob makes his first attempt at creating a model student. Bob uses random noise to create his first appearance. He lets out a nice animated Yahoo! And shows himself to Morty. Warning, warning, it's not that simple alert. For the sake of keeping this video concise, I skipped the following questions and replaced it with an almost laughably short example. I did this because, to be frank, if I explained all of these questions and concepts in detail, this video would be over an hour long. Please check out the resources in my description down below if you would like to learn more about the following topics. Thanks for that explanation, Mr. Editor. Back to our example, Morty looks at the pixelated mess that Bob has turned himself into. He uses this input, compares it to all previous data and parameters, and asks himself, does this look like a model student? In this example, his answer is a resounding no. Woohoo, you're right, says the quiet narrator in the corner. Oh, did I mention there was a quiet narrator in the corner? The narrator, who also doubles as a freelance wizard on weekends, takes out his wand and smashes it against the ground. Suddenly, a second being, who we will call Snob, is in the room. Snob is an example of the perfect student. Like Bob, he can physically transform to anything he wants, as long as it fits Morty's description of a perfect student. The wizard/narrator says, now you must determine whether both Snob and Bob are perfect students. This example shows the fact that real images are also fed to the discriminator network in order to train the discriminator network. Now you may be asking, why do you need Snob in this situation? Can't you train our generator using only fake images? To answer this question, we need to remember game theory. The problem with this approach is that if you only use fake images in your model, the discriminator will quickly learn that every single image is fake and will make predictions accordingly. For reasons that we will learn about in a second, this would create a situation where our model would never improve. Now back to our example, Morty is slowly recovering from the shock of seeing a narrator that doubles as a wizard. Eventually, he picks himself up and begins to think about the fact that he was right that Bob was not a perfect student. He takes a deep breath and adjusts his learning to account for the fact that he was right. In comparison, Bob adjusts his learning to account for the fact that he was wrong. Both will now make better informed decisions next time. Warning, warning, it's not that simple alert. Here are topics that I completely skipped over. Again, this is a laughably simple example. Resources in the description if you would like to learn more. You know, Mr. Editor, if I didn't love you so much, I would say that your interruptions were getting annoying. This laughably simple example demonstrates the feedback loops that the generator model and discriminator model have. To put it simply, with each iteration of the game that is being played, the generator gets better at creating generated samples that fool the discriminator, and the discriminator is updated to get better at detecting real and fake generated samples. All this being said, we will now leave our friends and let them play this amazing game. We are back, and we have completely lost track of the amount of games that our friends have played. As we can see, Bob is still clearly a fake model-generated student. Let's leave him be for a little while longer. Finally, after an unknown amount of time, Bob finally tricks Morty. "Yes!" screams Bob. "I am finally free!" "Not so fast," says the narrator/wizard. "You need to trick Morty an average of 50% of the time." "Up yours!" screams Bob. He tries to leave the room, but he is blocked by an invisible wall. A tear rolls down his eye. Both Bob and Morty adjust their learning and continue the game. This example represents the principle that in order for a generator model to be considered good, it needs to be able to trick the discriminator at least X% of the time. You may be asking, what does X represent? Now, to be quite honest with you, in my research I found no standardized value, so 50% is an arbitrary value. If you have more knowledge on the subject, please comment down below. Bob has finally tricked Morty 50% of the time. Bob is finally allowed to leave the room. With swagger in his step, Bob walks up to the door. The invisible wall is no longer there. "Wait," says the narrator/wizard. "Fulfill one last request for me. Use everything you have learned to create the absolute, 100%, complete, outright, definite, absolute, and universal perfect student." Bob takes a deep breath and thinks for a second about who he will transform into. Bob digs deep into himself to create the perfect student. In a flash of brilliance, he knows exactly what he must do. He transforms, and instantly a smoke machine in the corner of the room goes on for dramatic effect. The smoke clears.
Whoa!
What the fuck? In all seriousness, this last example is meant to represent the fact that after all the trials and tests, when all is said and done, you should have a fully trained GAN that can be used for the purposes with which it was trained. In our example, Bob grew up to become a motivational speaker on how to become the perfect student. Snob became an elusive criminal mastermind that is now wanted on 13 counts of passive aggressiveness. GANs are truly one of the most fascinating technologies today, and if there is one thing that I hope this video accomplished, it's that I hope you are more interested in the enthralling world of machine learning. Please do more research into this topic with any of the links in my description, or watch another video on my channel. Bye!